Hello, Algebra 1 students. Welcome back to Topic 5 on piecewise and linear absolute value. Last class we made the jump from piecewise to absolute value, and really for the rest of this unit we're mostly going to focus on just absolute value until actually our very last lesson, and we're going to tie it back to piecewise again. So let's begin. You have an opener for today. The parent function of linear absolute value graphs is the equation f of x equals what? Oh, well, hopefully we remember from last class it's just equals the absolute value of x, right? We need to graph that equation below and then answer each of the questions. Now, when you graph this equation, we really just need to remember what this graph looks like. This isn't one where you should be substituting in numbers or thinking about tricks. You just need to know what this graph looks like. This graph has a point at 0, 0, and then it moves up to the right, up to the left, and the points are connected. It makes that V-shaped graph that we're hopefully coming to expect from our linear absolute value graphs. It looks like this every time. That is the parent function. It is our most important absolute value function. Now, the rest of these, we're going to start with domain and range. Our domain, as we discussed last class, for pretty much every function except for some different piecewise, is going to be all real numbers. So in this case, we could say that the domain is all real numbers. The fancy way, by the way, to write the real number symbol is with two bars and connect it down like that. It's double bar R. That stands for real numbers. Okay. Now, that's one way to write it. The other way that we can write it is we can say our x values go all the way over here because the graph goes infinitely wide, so they start at negative infinity, and they go all the way over here to positive infinity. Domain measures how wide the function is if you look at it from a graphical perspective. However, the range really measures the height of our function, and this function does have a limiting height. Well, maybe not a height because it does go up forever, but it has a limiting floor. The lowest it gets to me, let's see, this is 2, 1, 0. Looks like the lowest it gets is a y value of 0. And so you could describe the y values in two different ways. You could say the y values are equal to 0 or greater than 0. Or the other way you could describe it is you could say we start at 0, that's the bracket to show equals, and we go up to infinity. Both of those are accepted, and you need to be comfortable with both of them. But as a teacher, I don't care which one you write. Just be ready if it's a multiple choice test, you need to be able to recognize both. The last part of this asks you about f of 2, and hopefully we're getting comfortable with this by now. That means 2 comma what? Well, f of 2, we go to the input or the x-axis and think what y brings us up to the graph? Well, that is a y of 2. Same thing, f of negative 3, our input is negative 3. What is the output that carries us up to the graph? Well, that is positive 3. Alrighty, we're going to be working a lot today on Desmos, not the student.desmos.com, but just our traditional Desmos. Desmos has been a free software program for the last decade or so, and its big success story has been its graphing calculator. So they're actually, if you go to the to your app store, there are actually a couple different Desmos apps you can download. One of them is the scientific calculator, which I've discussed before, and maybe that's already on your phone. I hope it is. But then the other one is the graphing calculator. So we are going to go ahead and be using the graphing calculator of Desmos, and we're going to do that to better understand how to graph linear absolute value functions. Today is really all about shortcuts, so that we don't have to make those tables that we did last class. It's somewhat similar to how HK form and MX plus B are shortcuts for lines. So, first, some good news. We're actually only going to be graphing linear absolute value this whole year in HK form. And here's our general equation, right? Our HK form looks like this. It has to have these absolute value bars. If it didn't have those bars, if those were parentheses, then what shape graph would that make? Well, that would make a line. But as soon as we have those bars, now we know it's going to make a V. Second, you might notice that the slope, this number outside of x, our multiplying by x out here, is using the letter A instead of M. You can use either one. For some reason, traditionally with regular lines they use m, and for pretty much any other equation they use a. I don't know why. It's up to you. We'll all know what you mean if you use m instead of a. A just tends to be a little more popular, so if you want to start using it now, that's totally fine. So we are going to start with the parent function. So let's open up Desmos, and I probably should have started just at Desmos. So here's Desmos, and you're going to open up the graphing calculator, or you can download the app on your phone and open it up there. So here's our graphing calculator. I'm going to change my screen so it's a little bit more zoomed in, and let's begin. So start with the parent function. We're going to graph f of x equals the absolute value of x. Now don't forget, if you don't want to type f of x, you can just type y. Now, I'm going to show you how to do this on Desmos in a couple different ways. First, and my favorite way to graph is just using a regular keyboard. And I have that same keyboard I did before. So I'm just going to type everything on here. I'm going to do f of, you have to do the shift right there, x, and then equals. And then the absolute value bar is actually this guy that's right here. Sometimes this key is shifted up or to the left, but you usually have to do shift and then that key. So that's going to be the absolute value. So when I type this in, I'm going to do f of x equals the absolute value of x. And you'll see that hopefully starting to become familiar, parent function. Now, other ways we can do this, we don't need to type f of x. You can just type y. The advantage of typing f of x, though, is if you go down to another line and you type in like f of -3, it will actually tell you where the point is. Or if you wanted to be really fancy, you could type out the point -3, comma f of -3, and it'll even put the point on your graph. So I really do like f of x. Now, if you're on your phone and it's forcing you to use the keyboard that's on Desmos, that's totally fine, right? Let's get rid of my graph and we'll try another one. You can either use y or f of x. Y tends to be a little faster then. Y equals, and then here's your absolute value bar of x, right? Same idea, but I'm going to switch it back to f of x. There we go. So we have our parent function. Now, graph the parent function in the form of f of x equals a blank, and a blank, right? We're filling in a, h, and k. You're going to need to fill in numbers and operations like plus or minus in those blanks above to make the same graph as f of x equals the absolute value of x. So it's going to look like this. We're going to do a new graph. There's going to be some blank that goes there, and some blank that goes here, and some blank that goes here. Now you might think, ooh, maybe a 0 goes here. There needs to be a number up. Now we can tell that my purple graph doesn't match the green anymore. All right, I think eventually, though, you'll probably figure out that this needs to be a 1, and it still matches. Then you're like, oh, maybe I add 1 here. Oh, nope, 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 nope. It doesn't match anymore. What can you add that won't change an equation? How about 0? And then I bet you'll get it from there. We can also do plus 0. Notice this could be a -0 as well. That doesn't matter one way or another. So it looks like our blanks would be something like this, 1, and then we can do x minus 0, plus 0, or any combination of those pluses and minuses. F of x equals the absolute value of x is known as, we've said this a million times, and I hope it sinks in soon, the parent function for linear absolute value. The reason it's known as the parent function is because in HK form, the absolute value of x has the most basic slope, which is our m or our a, and that's equal to 1. 1 is our absolute basic slope. You might say, well, what about 0? That's true, but 0 is always going to be flat, so it's, I think we're going to go with 1, especially because it's multiplying as our most basic. Additionally, h and k both equal 0. And this really tends to be true for pretty much any parent function, and we're going to learn several more parent functions next semester. Whenever a is 1 and h and k are 0, we say that that is the parent function. We also say that h comma k, which equals 0, 0 in this case, right, is the vertex of our linear absolute value function. Now, hopefully we've learned the term vertex before. If you haven't, you're about to learn it now. A vertex is this sharp point where two lines or line segments come together. A lot of times you talk about them in geometry. You might have like a hexagon that's with 6 sides, and you might say, oh, so if I could draw a hexagon, I should have picked an easier shape, but oh well. 1, 2, 3, 4, 5, 6, there's my hexagon. They might say how many vertices, the plural of vertex, are there on this hexagon. You're like 1, 2, 3, 4, 5, 6. That's where everything comes together, right? Okay, now, let's get tricky. For each equation below, explain what the vertex is without graphing, and then use Desmos to graph the equation to check your work. So take a quick second, see what you can do, and then we'll come back together. I'm actually going to do the opposite here. I'm going to graph and then see if we can figure out the pattern for the first one. So our first one is going to be, and I'll keep the parent function up there, why not? Y equals 1. It was x minus 3 plus 1. Does that seem right? Yeah. Very nice. Now the vertex on Desmos you can actually click on and it will give you the points. So it's 3, 1. Is there a way we could have gotten that without graphing? Well, hopefully you're saying, oh yeah, well that's just h and k, right? So we know that h is 3 and k is 1. Notice that h always still, even though it's not a line, still presents as the opposite. So I bet you can figure out the rest of these. -2, -4, and +31, -72. Okay. Now you also might notice that this one had a 1 in front, this had a 1 in front, and then I dropped the 1 over here. Do I really need to write the 1? No, we don't, right? Because whenever 1 is multiplying, it is optional to write. And in fact, for today, we're always going to have an invisible 1 or sometimes a visible 1 in front. We're not going to use any other values for a or for m for that slope. Okay, so let's go ahead and take a peek at this next part. On Desmos, please type the equation below. Okay, so our equation looked like this. It was y equals absolute value x minus h plus k. You'll notice nothing shows up, and that's okay. That's what's supposed to happen. We need to know a few things about the equation above. First, the value of a, and as a reminder, a is like the slope. The guy that's hiding here is going to be 1. Second, h and k are standing in for numbers, right? Clearly they are not numbers, they're letters right now. And what we're going to do is we're going to add what are called sliders. Sliders are going to assign a temporary value for both h and k. So you could either click h and then click k, or you could say add sliders for each. Now we have a graph that's shown up. Okay, so what are they asking us to do? What does Desmos say the value of h and k are currently? Well, that means if we take a look, doesn't it say that h equals 1 right here, and k also equals 1? So h equals 1 and k equals 1. That means then that our current equation has that invisible 1 hiding, h is 1 and k is 1. That is not our parent function. But let's go ahead and quickly graph that based on the graph we see on Desmos. What do we need to graph? Well, we need certainly the vertex. Our vertex is 1, 1. We could have gotten that from our equation. And then we need to know how steep each of the sides are. And for today, it looks like we go up 1 over 1, up 1 over 1 all the way through, and up 1 left 1 on the other side. So just putting in the rest of these points here, we have our absolute value graph. The vertex of my equation is 1, 1. I know this because on the graph, well, I don't know how you want to say it, the pointy part is at 1, 1. And I know this because in the equation, h equals 1 and k equals 1. The domain, well, how wide does this graph get? It goes forever in each direction, so this graph gets infinitely wide, so we're going to say it's all real numbers. Or you could use that double bar r, or you could say it goes from -infinity to infinity. The range for this graph, though, is different. The range can be a little trickier. Our range here, well, it definitely goes up forever, but it has that floor, that limiting factor. The lowest it ever gets is a y of 1. So you could say y is greater than or equal to 1. Or you could say it begins at 1 and goes up infinitely far. Okay, now sketch in the graph of the parent function for absolute value, and I'll do that in green on the graph above. Well, my parent function, we need to have this memorized, starts at 0, 0, and goes up 1 over 1, so it actually matches a lot of this equation, right? Looks like this, and then like that. The two functions on our graph are certainly related. So if I asked you to start with the green parent function, how could you pick up the parent function and move it to perfectly match the yellow graph, that x minus 1 plus 1? Take a quick second and answer that. Well, hopefully you said that you would just take this whole function and you would move it up 1 and to the right 1, right? If you took every point on here, if I took this point and moved it up 1 to the right 1, it'd match to that one. Up 1 to the right 1, it'd match there. If I took this and went up 1 to the right 1, it would match. Okay, so what do we do with that knowledge? Well, the idea of moving the parent function to create another graph is known as translating or sliding or moving the parent function. We use the terms horizontal and vertical, sorry about that, and vertical to describe which way the graph has been translated. Sometimes you'll also hear someone say shifted to. So let's quickly explore how h and k translate our absolute value function. I'm going to go back to Desmos, and I'm going to go ahead and hit the play button over here for h. And what that's going to do is it's going to move my h values up to 10, and then back down to -10, and then up to 10, back and forth, and it's going to let us see the effects on the graph. So I'm going to hit play, and you can see it moving. How would you describe the movement of that graph? Well, hopefully you describe that movement as horizontal movement, side-to-side movement. So in this box down here, explain how h translates your graph. You could say side-to-side or horizontal or anything like that. All right, let's go ahead and see what happens if we adjust k. I'm going to move h kind of back to the middle, and now let's move k. Well, as we vary k, as we change k, notice that our absolute value function is doing what? Well, it's moving straight up and down, right? It's the vertex is staying put horizontally, but it is sliding or shifting or translating vertically. Okay, so get those thoughts jotted down, and we'll do a quick conclusion. Horizontal shift or movement along the x-axis is caused by h. Be careful, in HK form, just like with lines, we always use the opposite sign of h, and that's because the equation has a minus in here, and so when you use a number, it's always going to switch to the opposite. Vertical shift, or up and down movement, is caused by the k value. And again, for today, don't let a worry you. It's the same thing as m. It's the slope, and we're just going to use a slope of 1. So let's go ahead and get some extra practice in. The graph of the parent function, which is f of x equals the absolute value of x, has already been given to you. Do you guys see all 6 of these have the parent function graphed? You are going to get a new equation. And do we see the new equation for each one of these? You're going to identify ah and k and the vertex, explain how the parent function is translated to create the new function, and then graph the new function without Desmos. Desmos is a great tool to understand what's happening and even to check your work, but you're not going to get Desmos on the test. Sorry. So here we go. Let's look at this first problem, and then hopefully you guys can take care of the rest. Well, the vertex here is +3, +1, right? And we also know that for today, a is going to be 1, so h is 3, k is 1. All right. Well, let's see if we can answer that question. Because h is 3, where am I going to move this parent function? We're going to move it 3 units horizontally. And k is 1, so I'm going to move that 1 unit vertically. So if I take the vertex here, and I go ahead and I move that 3 units horizontally, that means 3 to the right, over here, and then 1 unit vertically, that gives me this spot, which is not coincidentally also the point 3, 1. Then, if you were to take every other point and do the same thing, it would also make that V-shaped graph. Now, of course, you could also say, well, since the slope is up 1 over 1, couldn't I just do this? And yes, you absolutely could. But it's always interesting to think about this in terms of shifting or sliding or moving horizontally and vertically. So why don't you guys go ahead and try these others. They go pretty darn quickly. Then once you're done, if you can check your work if you'd like. If there's any you stuck on, you can skip to those, and then we'll move on to the last page for today. All right. Second problem. Vertex -1, 3. A is still 1. H is -1. K is 3. That means that my parent function will be shifted -1 units horizontally. That means to the left. But k is 3 units vertically, that means up. Left 1, up 3 is right here. That's my new vertex. And every other point is going to follow that same pattern. And it's going to continue to make our V-shaped graph. Third one, okay, we have positive 1 comma negative 3. A is still 1 for today. That means we are going to shift our parent function 1 unit horizontally and negative 3 units vertically. And I did completely wrong. 1 unit horizontally and negative 3 units vertically, which is the point 1, negative 3. From here, you can use that up 1 over 1 slope, or you can move every point 1 unit horizontally and 3 units vertically. There we go. All right, one more of these. We have negative 3, negative 1. A is 1, H is negative 3, K is negative 1. Guess I should stay consistent with those ones, huh? And I just noticed it more when there's absolute value because they look like ones as well. So we are moving negative 3 units horizontally, negative 1 vertically, negative 1, 2, 3, negative 1. There we go. And then using that same slope. Perfect. 2 to go. Uh-oh, curveball coming at us. X minus 2. Well, it looks like we definitely have the number inside the absolute value, and the number inside the absolute value is always the h. So we have the h, we do the opposite, that's 2. A is 1, h is 2. But what about if there's no number at the end? Well, the parent function has no number at the end. And so we need to recognize that because the parent function's at 0, 0 for the vertex, that just means there's an invisible 0 at the end. That means we're moving 2 units horizontally and 0 vertically, so to the right 2 and up 0, and then we use the slope from there. Perfect. Once we're here, we're moving on to our last question, problem 6. 6 gives us this marvelous absolute value of x minus 2. A is still 1, but then the question becomes, is this minus 2h or k? Well, looking back up here, the number inside absolute value has to be h, outside has to be k. This number is on the outside of absolute value, that has to be k. So what is h? Well, again, the parent function is at 0, 0, which means that there is an extra 0 hiding inside if you see nothing there. So you could rewrite this with the 1 on the outside, x minus 0 minus 2, to see that h is 0. So we shift 0 units horizontally, negative 2 units vertically, which starts us right here, and then up 1 over 1 in each direction. And that was off. There we go. All right, we finish this guy off with a little bit of a squiggle. And that's not going to slide. There we go. Good enough. Okay. Hopefully you're feeling pretty confident on graphing these functions. So, just like with everything, let's try the reverse. We're going to first describe, without graphing, how our parent function has been transformed or translated. So, based on this, which way does the parent function move? Well, h is 2, k is negative 2, so we move 2 units horizontally and negative 2 units vertically. This guy, we can always put the plus 0 here. H is going to be negative 8 and k is 0. We've moved negative 8 units horizontally, that's to the left, and then 0 units vertically. And last but not least, we should be able to recognize there's that invisible 0 hiding in front. So h is 0, k is negative 7. So we move 0 units horizontally, but negative 7 units vertically, which is like 7 units down. To finish off the day, you are given 4 different absolute value graphs. You need to identify the vertex and then write the equation for each one. Good luck, check your answers at the end, and that's all I have for you today. Ready, set, go. Alright, and we're back. So let's start with the vertex, and I think the vertex for each one isn't bad. This is negative 2 comma negative 3. This vertex looks like it's 1, 1. This vertex is 0, negative 3. And this one looks like it's negative 1 comma 0. Halfway done. Next up, let's write that equation. Remember, our equation is going to be in HK form, and there is that invisible 1 that's hiding out front. Okay, and then we're just going to use our h and our k. So we can do x the opposite of h, and then whatever k is. Now realize, if you did it the way I did, you're actually wrong. And the reason you're wrong is, hopefully you spotted it, I used parentheses instead of absolute value. What would this graph look like? Well, I'll show you really quickly. This would still start at the right point, and it would definitely go up 1 over 1. But it would look just like this in each direction. So instead of graphing that V-shaped graph, what we did instead is we made a line. Because we have only graphed with parentheses all semester long, we've only done lines. But now we've entered that absolute value realm, and so we do need to put the absolute value bars to actually make our graph take that V shape, because absolute value will turn things positive on both ends of our graph. Notice too that you could have left the 1 off in front, and I will leave the 1 off in front for the rest of these, just to be succinct or efficient or write less. All right, let's look at our next one. Our equation, we need those absolute value bars, and notice these look like absolute value bars. I wasn't consistent with my ones here. X minus 1, opposite of h, plus 1. Our third one, okay, absolute value of x minus 0 minus 3. And I think the more efficient way to write this is to leave off that minus 0 and just say it's the absolute value of x minus 3. Last but not least, the absolute value of x plus 1 plus 0. And again, you would see most people write this as just the absolute value of x plus 1, no plus 0. So hopefully you're feeling a little bit more confident on graphing absolute value without using a table. Again, we started with the idea of what a vertex was, and we also talked about those shifts or those slides horizontally and vertically, H and K, and we're going to come back to those all year long, especially second semester. And then we practiced a little bit, both graphing and then writing equations. So thank you for tuning in. Next class, we're going to explore the a value or the slope a little bit more for our absolute value graphs. Hopefully you're finding some success here, and I'm excited to see you back for 5.5 absolute value transformations.